Okay, so the Kruskal-Wallace is the non-parametric version of the one-way independent ANOVA, the one that we kind of the first ANOVA that we did, which we sometimes call the completely randomized design ANOVA. So we have just one factor, no blocking factor, no second factor. And it's very similar to the Wilcoxon rank sum set test. So I'm going to start off, I'm kind of going to show you some data. So we basically, what we're doing with this one is we've got 3 different hospitals. And each hospital has a number of free kind of free beds at a given time. So we're just making these observations of beds available at the hospitals. And what we can see is we basically put all the observations in order, regardless of whether it's from hospital 1, hospital 2, or hospital 3. And then we rank them as we've been ranking for the other tests. So the hospital with 0 beds free gets rank 1, 3 beds, rank 2, 4 beds, rank 3, 5 beds, rank 4. And again, for example, this is rank 9 and 10. They're both the same value, 13. So we aggregate and we get rank 9.55. Now, what we can do is we can have something for a rank sum of each of these hospitals. And all that is, just again using Excel, so if the hospital is 1, we basically just sum the ranks. So almost exactly the same as what we did for the Wilcoxon rank sum. So we've got the rank sum for hospital 1, the rank sum for hospital 2, and the rank sum for hospital 3. Then we have 10 observations for each hospital and 30 total observations. Just note the difference between those numbers, as that will be important in a minute. Okay, so we actually have a kind of a statistic that we use, and I'm going to go through to the full test in a minute. And this is this is actually distributed with a chi-squared distribution. So we're testing it against the chi-squared statistic. And all we're doing is we're basically summing each of our squared rank sums divided by the number of items in the group. Then we're scaling by the total number of items, 12 over n times n plus 1. And then we're subtracting 3n plus 1. You know, if you want to know how this formula was derived, then you probably want to take the entire semester non-parametric stats class in the statistics department. But since we only have a week, we can't really get into the derivation. The next kind of slide, and I just actually snipped it beforehand so I can comment on it. This is the actual hypothesis for it. So we have basically we're comparing, like, you know, k groups, in this case we're going to call it k probability distributions, and the null hypothesis is all k are identical and at least 2 differ in location. So this is the equivalent of the ANOVA alternative hypothesis, that at least 2 means differ. It's the same thing, but we're thinking in terms of the location of our probability distributions. Now ignore this test statistic and just go to the alternative at the end, which is much easier to calculate it. Because here we're just calculating average ranks for the groups and average ranks overall, so it's a little bit complicated. The key here is that we have a chi-squared. So it's a little weird, it's like an ANOVA, but it's working similar to our chi-squared test of a multinomial test with k minus 1 degrees of freedom. And basically we're testing our H statistic against the chi-squared. Okay, so we might as well go ahead and do this test for the hospital and then just give you the conditions. The K samples are random and independent. Importantly, our groups need to be, you know, of reasonable size. There are at least 5 or more measurements in each sample. And the underlying probability distribution should be continuous. Okay, so let's kind of go back to our kind of the cut of the slides. So I just get the right one. Okay, here. So let's just do this for the hospital. So H0. And let's just actually have this in black. So H0. The probability distributions. For the K hospitals are identical. And again, you know for the exams, I'm not going to expect you to kind of write out longhand for this hypothesis. You can just use K probability distribution. So at least 2 of the distributions, and I guess we should put like 3 rather than K hospitals if we're going to adapt it. At least 2 of the probability distributions for the hospitals differ in location. Okay, so let's assume we've got this here. We've got our null hypothesis, our alternative hypothesis. Let's just say we're going to test with alpha equals 0.05. The test statistic that's going to be H is 12 all over. Now I'm actually going to use big N because it's the total, just to avoid confusion. Sigma I equals 1 to K, where K is the number of groups, and then Ri squared all over Ni minus 3N plus 1. And the rejection region, let's just go back up to here. And we're going to reject H naught if H is greater than chi squared. And we're going to test whether the alpha equals 0.05 with K minus 1 degrees of freedom. So here K is 3, so it's 3 minus 1, basically 2 degrees of freedom equals K squared 0.05 comma 2 equals, you might remember these values, but let's just go back to my statistical tables and find the chi squared. Alpha equals 0.05, 2 degrees of freedom is 5.99. Okay, so we're going to reject H naught if H is greater than 5.99. Calculate the test statistic. Okay, so we can actually do this from Microsoft Excel. So we can actually just kind of calculate this. So let's just say H equals 12 all over N plus 1. And then we're going to do the rank, each of the ranks squared. So this would be, and there's 10 in each group. So let's just fill this in already and see what we have. Now let's go back to my Excel sheet. So we've got 120, 210.5, 134.5. And each of these is squared. Minus 3 big N, so 3 times 30 plus 1. And again, you can see, here we use minus 3 times 30 plus 1. We've done each of the rank sum squared divided by the N, and then we multiply by 12 divided by total sum plus 1. So again, and our answer is 6.097. So that gives 6.097. So my conclusion, H equals 6.097 is greater than 5.99. So reject H0. So there's evidence at least 2 different locations. Now the funny thing is, and again, this isn't going to be on the exam. The post hoc stuff for non-parametric is not going to be on the exam, but you could actually then do something like the Bonferroni test, but with Wilcoxon ranked sums rather than independent samples of means. Okay, so that was kind of our data, and here's just this was just another this was the example from the notes. I kind of combined it all in Excel. So we have the hospitals, the number of available beds, and then the ranking. Okay, so we can also do it in SPSS. So we're going to do, I've actually got the data here. So we have the beds and we have the hospitals. And we're going to do analyze non-parametric tests again, independent samples. And we're going to set the fields. And we're going to have the test fields is going to be the number of beds. And we're going to group by the hospitals. And let's just do the settings. It probably would run this anyway, but let's just do the Kruskal-Wallace. And you can see that we actually have this ability to do the pairwise comparisons. So I'll show you that when we do the results in a minute. So here we go, let's run it. Okay, so you see, we got it right in Excel, the test statistics 6.099, just a little bit rejected. You can see that our p-value was 0.047 when, the test p-value is 0.05, so that actually matches with the test we did manually. And we get, rather than the mean plot, we actually get a box plot here, which shows the distribution for the hospital. So it looks like 2 has much more beds available than hospitals 1 or 3. And then you can see the pairwise comparisons between the hospitals using, you don't have the choices you had at Hanover, but it's using the Bonferroni correction. But it's maybe a little bit too strict because you can see the adjusted significance using the Bonferroni correction between 1 and 2, which is the biggest gap, has a p-value of 0.065. So we wouldn't actually reject the individual differences. Though, we're almost there, and I said the overall test was just about significant. Okay, so that was just our kind of non-parametric version of the one-way or Hanover or completely randomized design. We went through it by hand and then we did it in SPSS. So next we're going to do the a non-parametric version of the blocked ANOVA, so kind of like the paired, but for multiple groups.